Let's talk about linear functions with an introduction with EGTC. We briefly mentioned EGTC, which means equations, graphs, tables, and context. All four of these are representations of a function, and we're going to take a look at how this affects linear. Okay, so let's start. Linear really only has two components. A linear component really refers to a pattern. A linear pattern really is a pattern that repeats itself really in the same way over and over and over again. So numerically speaking, you could say a pattern that adds 2 every time, plus 2, plus 2, plus 2, plus 2, or that subtracts 3 every time, minus 3, minus 3, minus 3. That is linear. Linear is predictable, quite simple. It's the most simple out of all the patterns that we're going to look at, and most simple of all the functions that we're going to look at. I said linear really has two components because what I just described is what is known as the rate of change, right? And then linear also has another component known as the y-intercept, or the initial value, the value at 0. And that's really a starting point. So linear situations usually have some kind of starting point. So let's get right to it. So here's a linear situation. Imagine that you have $4 saved up, right? So this is your starting point. You have $4. 4 is your starting point, all right? And let's say that from those $4, you have a friend who demands $3 from you every single day, all right? So if you would start with those $4, and every day you're going to take away 3, and we're going to keep track of this, and we can keep track of it in many ways. So we're going to say that 4 is our y-intercept, or our starting point. And if I take away 3, I am left with $1. $1. So after one day, you only have $1. If we were to take away 3 again, well, that's back to 0. Take another one. You'd be down to -2. So you're in the hole $2, which means you've had to make some kind of loan. If we take away 3 after that, you'd be in the hole by $5. So -2, -3, -4, -5. All of this, I'm saying it very verbally, but let's take a look at what it looks like in Math 1. So in Math 1, we would represent this pattern as a function. G of x equals -3x plus 4. So look at where the components go. Your slope, or your rate of change, is going to be -3 because I'm taking away $3 every day. That's where you want to look at problems and see what's the rate here. Well, the rate is take away 3, take away 3, take away 3. And then you want to think, well, where was my starting point? In other words, my y-intercept, and that is going to be plus 4. So that's the way that you would write it in these functions. You might have heard of that before as y equals mx plus b, where m is the rate of change multiplied by your input x, and b is your y-intercept. Okay. And from this, we can ask the same questions that we have been asking. So what's g of 200 mean? In other words, what happens when 200 is the input? Or what about if g of x equals 200? What does that mean in context? So these are still some of the common questions that we ask, but it's important just to know how to form that equation. All right, so speaking of the equation, you can graph that, -3x plus 4, and I have some variables that I need to change up. Change some f's into g's. All right, but the evaluation and the solving work the same way as we've been studying them. All right, and that's that. Okay, graph. If you look at the graph of what -3x plus 4 looks like, it can also be connected to what we've been talking about. So look at your y-intercept. Your y-intercept is 0, 4. So your y-intercept is 4. And then you can keep track of the days. So after one day, you can trace after one day, you are going to have basically $1, right? After 2 days, you are going to be in the hole. You have -$2. After 3 days, you now have -$5. So that's how the graph works. You got your y-intercept at 0, 4, and then rate of change, if it's -3, we're going to go down 3, right 1, down 3, over 1. And we always move to the right because time is our independent variable, and time moves to the right. Time continues to elapse. All right. Last thing is take a look at this table. All right. When I make a table here on Desmos for g of x equals -3x plus 4, look at my values: 4, 1, -2, -5, -8. The cool thing about this is changing y over changing x, no matter what 2 points you choose, your rate of change is going to be the same. And that's linear functions, a quite simple concept to start off with.